problem about acceleration, but this time down an inclined plane, and that was 2-4. Okay, so if you go back to page on your packet, and we go to page 5, okay, we have a skier, page 5, number 10. A novice skier starts out in the bunny hill, okay? So, and the hill has a 12-degree slant to it. That's its incline, right? And I showed you in the videos how to come up with your acceleration when it's down an incline like that, didn't I? Right? So now what I want you to do is I want you to do the first row down while I check your chapter 2 stuff, your notes. Fill in the first row of the chart. So your chart looks like this. But there's 2 rows on it. And I'll give you a hint. The first thing you have to do is come up with the acceleration. Okay? But you should know how to do that from your notes. Okay, checking notes. So I've already checked up to 2-2. So I need to set 3, 4, and 5. 2.3. Okay, good. I didn't check your 2.2s either. Do you have those? Good. Okay. 2.3. Good. 2.4. And then 2.5. Good. That's 2.5. How about 2.3, 2.4? Okay, good. Okay. Joules. Okay. Is that? Yeah, that's 2.3. All right, I'll just put a note. You show me later. It was in class we watched that. Were you here? When I was out. 2.2. What did I see 2.2 for you already? I already saw that. I need 2.3 and 2.3 through 2.5. Okay. Okay. Good. 2.3. Okay, I got your others. Just 2.3, 2.4, and 2.5. Good. 2.3. Why not? Why? All right. Why wouldn't you get it done in class though if you had the whole class? Oh, all right. Should have watched it. Okay. All right. How about I don't have your 2.1. Do you have 2.1 on you? Nope. Okay. 2.3. Yep. That's it. 2.4. 2.5. Good. 2-3, 2-4. Who's finished the first part, the first column, the first row? No one? Brinson, right? And Kayla, want to show me those? Okay, good. I assume you two didn't do the work. So I have your stuff over there, like test corrections. So. You're a backwards goer. Yes, looks good. Mary. Let's see if I got your other ones. Yes, from 3. Now, when were you going to see me about test corrections? Tomorrow? X? G study hall. Is that today, though? Last period. Okay, get a note from me after. Well, if you haven't done, turn them in. 2-3, okay. 2-5, okay. 2, you get your notes? Okay, 2-3, 2-4, and 2-5, good. In the bin. Spencer? Why not? All right, well, show me tomorrow then. That's too bad, because we're going to be talking about it. Well, I don't think it's all right. Maya? 2-3 through 2-5. Except for Julia, I need to see 2-2 as well. Where's Julia? Julia, I already looked at yours, didn't I? Oh, no, you were finishing. You had to finish the 1? Oh, you had to find 2-4. Yes. Okay, you can show me tomorrow? Yes. 2-4. 2-5. Okay, good. Caroline? Okay. Okay, 2-4 and 2-5. Okay, good. Well, we're going to go over it. You have to watch the videos to know how. All right, who found the acceleration? Austin? No, you didn't. I'm sorry. Aiden? Other A? What did you do? I asked Aiden. That's all right. All right, so A parallel to the plane. I showed it through similar triangles, right? Remember that? And it's A, what we call A parallel, just because it's parallel to the plane. That equals G sine theta, right? So G is what? Minus 10 meters per second for each second, or meters per second squared. And then sine of 12 degrees. And we could ask our calculator what it is. I'll avoid the stupid joke. So 2.08 minus 2.08. Okay? Now, what else do we know with our skier here? Oh, bummer. Not working. Oh well. We'll just draw a skier. There they go. What else do we know? All right, so VI up here, starting from rest, it's going to go into thing of hay down here. That's the hay. That they put those there to stop the skiers from injuring themselves because they don't know how to stop on the bunny hill, right? How far down the hill is it? 50 meters, right? But that's going to be we know that this is 0 meters per second. That 50 meters, though, is what? Since it's downhill. Negative 50 meters for our delta S there. And were we given anything else yet that we need? Once they hit the hay barrel, we know this is 0.09 seconds. We'll fill that in after. Okay, so anybody know what we could find in the top row? Kendra? What? VF. Did you say VF? What equation will I use? Now that would be an equation, right, you should definitely have on your reference packet. If you don't have that on there yet, you should write that on there. So you would write that equation on your reference packet so that you have that when it comes time for the test, right? So VI is just 0. 2 times A, which was minus 2.08 meters per second squared, times delta S, which was minus 50 meters. So VF squared equals times 100. So 100, 208, right? Positive. So VF we're going to find by square rooting both sides, right? VF, the square root of 2.208 is 14.4. Now should it be negative or positive? Because both of those would satisfy the condition. Negative 14.4 squared is 208. Positive 14.4 squared is also 208. So which one is it? Joules? What? Positive. Well, let's think. What direction? It would be negative, right? Because it's going downhill. So negative 14.4 meters per second. Now what else can we get? What? Oh, sorry. I did it in the positive. Should be negative. It depends how you define plus negative, but I think it's more consistent to keep it negative. It makes more sense. Kayla? Okay, so what would I do for that? Right, and then since VI is just 0, that would give me minus 7.2 meters per second, right? I've used so many colors that they have no sense to them, what we knew and didn't know. What else can we find? Well, we're just, Paul, delta V, and what does that equal to? VOOF minus V, right? Oh, so that's just minus 14.4 meters per second. How long did the skier go down the hill? Or will we use the solve for that? Leanne? Okay, so A is change in V over change in T, so change in T equals change in V over A. right? Change in V is 14.4 meters per second, and A is minus 2.08 meters per second squared. 6.92. What are my units? Just seconds, because meters per second divided by meters per second squared, it's the same thing as meters per second times second squared over meters. Cancel, 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 seconds, right? Everybody follow that? So now you know how to get the acceleration, right? It's g sine theta on a plane, ignoring any friction at this point. We'll bring friction into play later. It changes the net force. All right, but now the skier crashes into the bale, right? And we have to analyze that motion of the skier hitting the, crust. Sorry, that wasn't supposed to take so long. There's that one. There's the old one. That looks better, doesn't it? Now, as it hits, what speed does the skier hit the hay bale with? Anybody know? Spencer? Negative 14.4 meters per second. Good. Now, the skier is going to come to a stop, so what's our VF? Do we know anything else? Well, we have the time. Yes. Well, let's find our average velocity. I already have the equation here for average velocity, just these two added together, and it's the same as it was up there. This average velocity occurred over 50 meters in 6.92 seconds. This average velocity only occurred in 0.09 seconds, right? So the distance has to also be much less, right? So we could get the distance now, can't we, from this? What equation would I use to do that? Taylor? Okay, good. So delta S would be V bar times delta T, which would be minus 7.2 meters per second times 0.09 seconds. .65 minus 0.65 meters. So that's how much the skier indents the hay bales, right? So that's the skis pushed up against it, splatted up against it. You see the skis and stuff? Yes. Well, it's really a negative displacement, and it's negative because it's in this direction down. So it's because it went in the negative direction. That's why. Delta V here, just to finish this up, would be this minus that, and a minus would give us a what? Positive. So my acceleration, or our acceleration, would be delta V over delta T. $160. Now, how is that possible? How can you have a positive acceleration, but she obviously slowed to a stop? Maya? Good. That's right. So you can, a positive acceleration, just repeating what you just said, is slowing down or speeding up in a positive direction or slowing down in the negative direction. A negative acceleration would be slowing down in a positive direction or speeding up in a negative direction. Okay? Now in this case, we have enough information to know, but you could be given something where you didn't know whether it was speeding up in the negative or slowing down in the positive. Okay? Good. So that brings us through 2.4. In 2.5, we had to interpret graphs. Okay? And the first thing is, let's just review it real quick, because I went through the video pretty quickly when we were doing it. If you have position versus time graph, okay? Well, I know that's a curve, but let's think of the slope of that. Say we found the slope down here in this region, and we could look at a slope up there. What's the equation for slope? I could probably ask one of the shadows. Is there a shadow that wants to tell me what the equation of slope is? M, change in real close. Just switch them, right? Good. Okay, so what is our y here? What's y? S, right. And what is x? So that gives us what? Which is average velocity, right? So the slope on a position versus time graph is the velocity. So let's say that together now. The slope on a position versus time graph is the average velocity. Good. All right, so let's say we then had our graph of velocity versus time. Now I could see that my slope started out high, didn't it? And it went smaller. So I would be sort of like up here and maybe down there. High slope, high velocity. Smaller slope, smaller velocity. Higher velocity, smaller velocity. Right? Now, so let's think of that. Well, what was their equation for the slope? Remember? Yes, you do. Change in y. I'm putting you on the spot, but that's all right. Next year you'll be all ready to go. What will probably happen now, if you haven't done this, what's going to happen when you go to math class in the next couple days? So you're going to cover it, right? And you're going to be like, oh, that's what he was talking about. Or maybe not. I don't know. But I bet you cover it by the end of the year. So what is our change in y here? Change in v over, now that's equal to what? A. Now our a's for us are always flat lines. So in this case, it would be, actually negative, because the slope's negative, isn't it? So we'll always have horizontal lines for our acceleration. So the slope on a velocity versus time graph is the acceleration. So by going down this way, we do slopes. So SVA slopes down. What was I going to say? Oh yes, the change, because we deal with constant acceleration. You can have a change in acceleration. It's a Katapovich. That's what they're called. That's the units of it. Well, that's what it's called, a change. Look it up. Well, what is a change in acceleration? It's a Katapovich. You don't believe me? I'll show you. We'll just go to Wikipedia. Let's see. Where is it? There it is. Oh yeah, not cat. It's just jerk. I was picking on you. Get it? A jerk is a change in acceleration. That was the joke. You get it? It's a bad joke, I know. She knows I'm kidding. Now, it sounded worse than it. It was just a way. So a change in acceleration is a jerk, but we don't do jerks. But you feel those, you know, when you change your acceleration really quickly. It's like when you're feeling that quick acceleration change on like a roller coaster or something. Okay, now let's go the other way. Say we have acceleration versus time, okay? Now, the area under the curve, actually, I want to bring this all down. Down here. What would be the area under this thing? What is it? Between the t-axis and the line. It's a rectangle, right? So base times height. And our base is what? T, and our height is A. And delta T times A is just our change in velocity. So to get from the area graph, area versus time, if we took the area, acceleration versus time, if we take the area of that, what do we get up? What do we get? Our change in V, so we can go up on this, right? So we had a positive change in V. So let's say we started with a V of like here, we changed it positively and went up to there, okay? Well, let's find the area. This is velocity versus time. So to get from area or acceleration to velocity, we do the area to go up on the graph. So here's this area. Let's not worry about the 1/2 and stuff. It comes out with the fact that it's average velocity. It's VI plus VF over 2. That's where it comes from. But let's take the area here. Area, we'll just do base times height. The base is delta T, and the height is, we'll just do average velocity. That's where VI plus VF over 2 comes in, right? You see that? So what is delta V times V bar? Delta S. So we get to go up this way. Now let's think of our delta, our S here. Because remember, going this way, it was the slope on this graph, position versus time, gives us velocity. So if our velocity here is low, our slope must be low. If our velocity here is high, our slope must be high. So we must have a lower slope, but it's positive. Low slope positive. This one would give us a higher slope positive, like that. And I can get this general shape of the curve just from the fact that I know that this is a low, starting low slope, going to high slope. So that's your review on that. Now we'll do a problem. We'll start it. We won't finish it today. We'll finish it tomorrow. And so this is on page 16. And they give you a velocity versus time graph. All right, so let me scroll down a bit. So I'll put the velocity versus time graph on here. What does it say the divisions on velocity versus time are? The time divisions are what? 1 second, okay. And it goes to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then what are the velocity ones? 4, right? So we'll colorize it. It starts at 12 meters per second, and then over the next 3 seconds it goes down to 4. We'll call that the red zone. Then it stays at 4 for the next 3 seconds. We'll do that green. And then for the next 1.5 seconds, it goes down to 0. We'll do that blue. And then in the next 3.5 seconds, it goes down to -8. We'll make that one purple. I don't know if that's exactly 1.5, 7.5 there. Yes. Oh, to put it into 2 sections? That's all right. I thought I came back, but, okay. But maybe I didn't. Who? Yeah. Okay. So I broke these two into 2 separate ones because I'm going to find the area under the curve in the x-axis or t-axis. So I need to get this area, and then I need to get that area. That's why. I'm just not exactly sure if that's actually 7.5. It looks a little bit over Like it should be a little bit more, but we'll use 7.5 as an estimate. I think it got shifted on the graph a little bit, but so to go up to position versus time, okay? How do I go up to position? We'll have the same time scale, okay? So we still have 2 seconds here. What am I going to do to go? I'm going to find the area. That's right. So I need to find the area of these 4 zones. The first one's going to be this thing. What shape is that? A trapezoid. Now, I'm not going to. I'm just going to do it as a triangle or rectangle, because that's easier. So the area under this, the total area, I'll just do A1 and A2. And that will give me how much I change in position. So the area under the curve gives us a change in position. So the first area is a triangle, 1/2 the base of 3 seconds and the height of 8 meters per second. Well, look at the units. They work too, don't they? Because seconds would cancel and you would have meters. 24 divided by 2 is 12 meters. Plus this rectangle here, that would be base, which is still 3 seconds, times height, which would be 4 meters per second. So that would be 12 meters. So we get a 24 meter change from that. Okay? That make sense? Because it's the area from the curve to the t-axis. So not only do you have this triangle, but we have this rectangle to get down. So the total area, AT, is both A1 plus A2. Now the green zone is here, and it's that one. It's just the base times height, 3 seconds times 4 meters per second, or 12 meters. So that's a change in S of 12 meters. And we have the blue one. Well, we'll pick it up there.